Okay, today we're going to speak about a technique that's very important in statistics, logistic regression. It's different than linear regression in that the dependent variable, y, is not continuous. The dependent variable has just it's categorical and has just two categories. So in simple linear regression, you have a continuous dependent variable y and predictor variable x, the independent variable, and you have this equation that relates y to x. That can be extended to where you have more than one predictor variable. That then gives you the multiple linear regression model. Now suppose the dependent variable is binary. It's categorical and just has two categories, one success, two failure. And we're interested in predicting y from a continuous independent variable. This is the situation in which you use logistic regression. An example, suppose we have a cream for curing acne. And it may depend on what its success might depend on the amount that's applied daily. So the values of y are just 1 or 0. It was successful or not successful. And the values of x, the dosage, daily dosage, ranges over a continuum. So this would be a case when you use logistic regression. Let P be the probability that y equals 1, the probability of success. This will possibly increase with the value of x. The ratio P over 1 minus P is called the odds ratio. It's the number of outcomes resulting in a success over the number of outcomes resulting in a failure. This quantity will also increase with the value of s. This will go from 0 to infinity. P will go from 0 to 1. The quantity log P over 1 minus P is called the log odds ratio. P, the odds ratio, P over 1 minus P, the log odds ratio, P log P over 1 minus P, they're all related 1 to 1. Example, suppose I roll a die. The probability of rolling a die, or suppose success is that I roll a 6. The probability of that is 1 over 6. The odds ratio is 1 over 6 over 1 minus 1 over 6, which works out to be 1 to 5. So if you roll a success, 6, that's a success. The number of successes over the number of failures is 1 to 5. The log odds ratio is the logarithm of 1 over 5, logarithm 0.2 minus 1.69044. The logistic regression model assumes that the log odds ratio is linear related to x. You can't have P linear related to x because eventually on the right hand side, P will get out of the range 0 to 1. P ranges from 0 to 1. P over 1 minus P ranges from 0 to infinity. The logarithm of P over 1 minus P ranges from minus infinity to infinity, so it could be linear related to x. That allows for the possibility that log P over 1 minus P could be anywhere from minus infinity to plus infinity. Now, if I solve this back in terms of P over 1 minus P, just take exponentials on both sides. Then you can solve for P in terms of X. P over 1 minus P, e to the beta naught plus beta 1x. Bring the 1 minus P over here. Bring everything with P onto the one side. We get an equation for P. It's e to the beta naught plus beta 1x over 1 plus e to the beta naught plus beta 1x. If you graph that, that will form an S-curve. The limiting value will be 1. The value at 0 is e to the beta naught over 1 plus e to the beta naught. So the parameter beta naught determines the intercept of that S-curve. The parameter beta 1 can also be interpreted. When P is equal to half, that means that beta naught plus beta 1 x has to be 0 for that to be true. X equals e to the minus beta naught plus beta 1. So beta 1 together with beta naught will determine when P is equal to 1/2. That'll be at minus beta naught over beta 1. Another interpretation of beta 1, using calculus, you can show that the derivative of P with respect to X is equal to beta 1 over 4. So beta 1 over 4 is the rate of increase in P with respect to X when P is equal to 1/2. So it's the slope of the tangent line to the curve, the S curve, at when P is equal to 1/2. The data. The data for each case will be a value of X together with the value of Y. The value of Y takes on only two values, 1 or 0, whether it's a success or a failure. Suppose we've collected the data on 250 cases. So this is some of the data showed in an Excel file. You have a value of X and a value of Y, which is either 1 or 0. Estimating the parameters. This is very difficult, actually, and it requires a computer package. It will find the best estimators of the parameters. The parameters are beta naught and beta 1. So if you have your data in SPSS data file, you'll have a column giving you the value of X and the one giving you whether it's a success or a failure. To perform logistic regression, you go analyze, regression, and then pick binary logistic. Then up comes this dialog box. It wants you to identify the dependent variable. That's the variable that's either 1 or 0. And the covariate, this is the predictor variable, the continuous variable that you're trying to predict Y with. Press OK, and it'll carry out the analysis. Here's some of the output. The important thing is here, this gives you the estimates and their standard errors of the coefficients beta naught and beta 1. The constant is the value of beta naught. The B for the X value is the value of beta 1. So the parameter estimates, there's beta 1, 1.0309. There is the constant term, that's the value of beta naught. These are also standard errors, standard deviations of those that are used for testing. To interpret the parameters, e to the beta naught over 1 plus e to the beta naught, that's the intercept, that's the probability of success when x is equal to 0. So in this case here, beta naught was minus 2.0475, e to the minus 2.0475 over 1 plus e to the minus 2.0475 works out to be 11.343. So that's the probability of a success when x is equal to 0. The interpretation of beta 1, that will determine when the probability of success goes up to 50%. Minus beta naught over beta 1 will be the value of x that will result in the probability of success being 0.05. 1.986 in this example. Another interpretation of beta 1. If you divide beta 1 but divide it by 4, that's how fast p is increasing when p is equal to 0.5. That's the slope of the tangent to the curve when p is equal to 0.5. So in logistic regression, you have a binary dependent variable, a dependent variable that just takes on two values, 1 or 0, 1 for success, 0 for failure. And we're interested in predicting y from the value of x. Mainly, we're interested in computing the probability of y equals 1 for different values of x. The logistic regression model models linearly the log odds ratio as it's related to x. P is the probability of success. P over 1 minus P is the odds ratio. The log odds ratio is the logarithm of that ratio. The logistic regression model assumes that the log odds ratio is linearly related to x. So then you can solve for p over 1 minus p. It'll be e to the beta naught plus beta 1x. And then you can solve for p. P will be equal to e to the beta naught plus beta 1x over 1 plus e to the beta naught plus beta 1x. When you found beta naught and beta 1, you can actually plot this graph, p versus x, to show what those two parameters mean. That's what the graph will look like. It'll be an S curve. When you found the values of beta naught and beta 1, compute for different values of x, p, and draw a curve through that value. That will asymptote out at 1. Back here, it'll cross this axis when p is equal to e to the beta naught over 1 plus e to the beta naught. The multiple logistic regression model. Here now we're going to try and predict the log odds ratio, log p over 1 minus p, not on the basis of one variable, but on the basis of several variables, x1, x2, up to xp. You can then solve this equation for p, and this is how it'll be related. An example. In this example, we're interested in determining whether a premature baby develops this condition, bronchopulmonary dysplasia. So we're interested in a predictive model which will determine the chance that a premature baby will develop bronchopulmonary dysplasia from 1, its gestational age. That's the age of the child from conception, and its birth weight. We'll be able to see that the chance of it developing that condition is less if its gestational age is longer. Mainly, it's not as premature as could be, and its birth weight. If it has a higher birth weight, it'll have a less chance of developing this disease. So data was collected for 223 infants. What was measured was the gestational age, the age in weeks from conception, the birth weight in grams, and whether or not it developed bronchopulmonary dysplasia or did not. So there's the data in a data file. There's the results of performing logistic regression, predicting whether it developed PPD from birth weight and gestational age. There's the equation, 16.8528. That's the constant term. The weight of birth weight is minus 0.003. The coefficient for gestational age is minus 0.505. From this, we can develop an equation which gives you the probability that it'll develop bronchial PPD from birth weight and gestational age. Here is some graphs showing the risk of BPD versus gestational age and birth weight. The different colors are different gestational ages, going from the smallest 27 weeks to 32 weeks. Along this axis here is the birth weight. This is gestational age, the different graphs here. So you can see as birth weight goes up, the risk of developing PPD goes down. So from that graph, somebody could say if the birth weight was 1,300 and the gestational age was 28, then the chance of developing bronchopulmonary dysplasia is 40%. Today's lecture is going to be short. The last assignment, computer assignment, involves two problems. One is fitting a linear model with more than two variables. There's another one where you're using logistic regression to predict a categorical, a binary dependent variable from one independent variable. So we'll, at this point, stop the lecture and I'll go over how to do those problems in the lab on Monday. So on Monday, we'll tackle the last topic in the course. It's non-parametric statistics. Most statistical methods assume that the data follows some probability distribution. The usual distribution is the normal distribution. So the distribution of the observations is known except for a finite number of parameters. This is called a parametric model. Non-parametric model is when you don't make those assumptions. So the last topic will be looking at techniques that assume a non-parametric model, and we'll look at those later on. So at this point, we'll end the meeting.